Okay, so this is 2022 time zone 2 paper 1 topic 5. It's the first question. A rectangular coil of wire RSTU is connected to a battery and placed in a magnetic field Z directed to the right. Both the plane of the coil and the magnetic field direction are in the same plane. What is true about the magnetic force acting on the sides RS and ST? So we want the magnetic force here. Let's say we can draw a point there and draw a point here. So first we know that conventional current flows from positive to negative. So this is positive, this is negative. So we know that the current will be flowing this way, this way, this way. Okay. So they want, let's first look at RS. The force acting on RS. So for this you would have to use your right hand rule for a moving charge in a magnetic field. So the current is pointing downwards and the magnetic field is pointing towards the right. So if you position it this way, you can see that your thumb, the direction of the force is pointing towards you. So it's out of the page. So we can straight away eliminate these. Now the force on ST. For ST, there is no force that acts because if you try to use your hand rule, you cannot position it so that the current is moving left and the magnetic force is up, and it is not on the direction of the not on the field lines as well. So so it's B. Next question. A circuit consists of cell EMF E equals 3 volts and 4 resistors connected as shown. Resistors 1 and 4 are 1 ohms and 1 ohm, and the resistor R2 and R3 are 2 ohms. What is the voltmeter reading? Okay, so we know the EMF is 3 volts. So let's say we take a loop this way. So at the end, 3 volts have to decrease. So at the end over here, 3 volts have to be used up. So let's say the current flows this way across that loop. So it will pass here and then here and then we'll go here. But let's say it went this way, it will go here and then here. So if it once but the current does not flow through here. So let's say it goes through this way. So after R1, 2 volts will be remaining. But then let's say it went this way, 1 volt will be remaining. So we can see on this side there's 2 volts and then this side on 1 volt. So the potential difference would be 2 minus 1. So it will be 1 volt. So the answer is B. Next question. A battery of negligible internal resistance is connected to a lamp. A second identical lamp is added in the series. What is the change in potential difference across the first lamp, and what is the change in the output power of the battery? So, let's draw the first case. In the first case, there is only one resistor, but in the second case, there is 2 resistors, technically, because a lamp would have resistance. Uh, so if there's one more resistor, so let's say in the original case we had V and then V here. Oh, sorry, just V. But if you add one more resistor, the resistance would be split across it. So it would be V by 2 and V by 2. So as you can see here, the change in potential difference across would be less. We would decrease because it's being split between 2 resistors. So it cannot be C or D. Now the output power of the battery. So we can use the formula P is equal to IV. So in the first case, P would just be IV. But we know that I is also equal to V by R. But in the second case, since we have two resistors, the resistance would be twice. So in the second case, it would be V over 2R. So now if we equate this for the second case, you would have V times V over 2R. So this would then become V squared over 2R. So you can see here that the power what was initially is being divided by 2. So the output power of the battery is also decreasing. So the answer is A. Okay, last question. A charge Q is at a point between two electric charges Q and Q1. The net electric force on Q is 0. Charge Q is further from Q than charge Q2. What is true about the signs of charge Q1 and Q2 and their magnitudes? So straight away with this question, we can assume that the signs of Q1 are the same because let's say we had an opposite charge. Let's say this was negative, this was positive, and this was, let's say it's positive as well. It doesn't really matter. So then in this case, this would be attracted this way, opposite charge, and this would also be repelled. So in that case, it doesn't work. So the only case we can assume is when the signs are the same. We can take, let's say this is negative, negative, or positive, or positive. It doesn't really matter. So we can eliminate these options. Let's check the magnitude of Q1 and Q2. Now, you know that the electric force is Q1, Q2 over R squared. So as the radius increases, the electric force would decrease. So you can see that Q1 is at a greater distance to Q than Q2, but we know that the net force is 0. So for the net force to 0 and the fact that Q is further away, the magnitude of charge of Q would have to be greater than Q2 because it's at a greater distance. So it would need more. We need a greater magnitude to make it cancel out. So the answer is A.